So we have Olya Mandelshtam talking about formulas for Macdonald polynomials arising from the ASEP.
So I want to first repeat what others have said. Thank you so much to the organizers for making this happen. And it's also really wonderful to see so many people being able to attend this conference. So I'm really excited to be a speaker here. So my talk today is based on work with Sylvia Cortell, Jim Hagland, Sarah Mason, and Lauren Williams. So it will consist of 3 parts. So first I will describe the asymmetric simple exclusion process, which is a particle model from statistical mechanics. Then I will talk about symmetric functions and Macdonald polynomials. And finally, I will talk about how the first 2 parts are related through the combinatorics of multiline queues. So let's start with defining the ASEP. So this is a particle model that describes particles hopping left and right on a one-dimensional lattice. So in our setting, the lattice is finite, but it can also be infinite in theory. So here we have 1 particle per site. So in this case, the particles can be either black or white. And at each time step, so we have a discrete process here. So at each time step, any 2 adjacent particles can swap with some probability. And if there is a boundary, then there can be interactions at that boundary. So the ASEP was originally introduced in the 60s, but independently by mathematician Spitzer and a team of biologists, Macdonald, Gibbs, and Pipkin. So it was originally studied as a model for translation and protein synthesis, and it was also studied as a model for other transport processes. So for example, for a model for traffic flow. So the ASEP is a canonical example of a non-equilibrium process, and since its introduction, it's been very widely studied. So it's been studied both for its applications and also for its many connections to other fields in mathematics and statistical mechanics. And in particular, it has some very beautiful combinatorial structure. So some of that you will see shortly. And also some deep connections to orthogonal polynomials, which I will also talk about. So in today's setting, we study the multi-species ASEP on a circle. So what this means is that our lattice is on a circle, and we have L species of particles, or sorry, L plus 1 species of particles labeled 0 through L. And we say the type of the ASEP is given by a partition where we just arrange the types of the particles in order. So here we have 1, 3, 3 2s, a 1, and 3 zeros. So this is what our lambda is in this case. And so the ASEP of type lambda is a Markov chain whose states are rearrangements of the parts of lambda. So these are all compositions that rearrange to lambda. So our convention is to read this, this state from the top particle clockwise. So here it's 1, 2, 2, 0, 0, 0, 3, 2. So that's our composition representing this state here. And the dynamics of this model are swaps of adjacent particles occurring at rate 1 or t, where t is a parameter between 0 and 1, depending on which particle is larger. Okay, so the main question, or the first question that one would ask about a Markov chain is, what happens when we run this Markov process for infinite time? So this means, in other words, what are the stationary probabilities of this process, which we can compute as the eigenvector corresponding to eigenvalue 1 of the transition matrix. So here's a quick example. So let's take the ASEP with 2 2s, a 1, and 2 zeros. And let's look at all of the outgoing transitions from this particular state. So for example, if we swap the 2 and the 0, then we get this one with probability 2 over 5. So the over 5 is just to make sure that the sum of all of these outgoing transitions is 1. Now we complete the picture by drawing all the other arrows and all the other states. And then we do some linear algebra to compute the stationary probabilities, which turn out to be these very nice polynomials in T with positive integer coefficients. And so this 1 over z here is the normalizing factor. So we can write it as the sum over all of these unnormalized probabilities. And it's also called the partition function. So the partition function plays an important role when we talk about these processes. So our goal is going to be to study the combinatorics of these polynomials. Okay, so now I'll move on to part 2 of my talk. So I'll give a very brief introduction to symmetric functions as a warm-up to Macdonald polynomials. So polynomial is in n variables is symmetric if it's invariant under permutation of its variables. So here are 2 examples of symmetric polynomials, and we denote this space by lambda. And there are several nice bases of symmetric polynomials. So for example, m lambda, the monomial symmetric functions, and s lambda, the Schur functions, and all of these are indexed by partitions. And I chose the Schur functions specifically because because this is actually a very natural basis. So let's take the standard inner product on the symmetric functions. Then the Schur functions can be defined as the unique basis that is orthogonal with respect to this inner product and upper triangular with respect to the monomial symmetric functions. So this was not a very illuminating way to describe what Schur functions actually look like. So for that, we need the combinatorial description of Schur functions, where we can write them as a sum over a certain fillings of certain tableau. So in this case, it's a sum over semi-standard fillings of Young diagrams of shape lambda. So here's an example of S21. So the reason I just spent all this time talking about Schur functions is because my favorite way to think about Macdonald polynomials is as a QT generalization of Schur functions. So Macdonald introduced Macdonald polynomials in 1988. So, and we can describe them as polynomials that are uniquely determined by the following properties. So they are an orthogonal basis for symmetric functions in the variables q and t with respect to the Macdonald inner product, and they are upper triangular with respect to the monomial symmetric functions. And analogously to the Schur functions, there is a tableau formula where tableau have q and t weights, and so we can describe these polynomials as generating functions over a certain fillings of these tableau. And this formula is due to Hagelin, Heyman, and Lur from 2005. And here's an example of a Macdonald polynomial. So this is what P21 looks like. Okay. So here are a few properties. Macdonald polynomials. So they are a, so they are is specialized to shear functions at q equals t, Hall-Littlewood polynomials, Jack polynomials, and in general, they're very nice because they generalize a lot of important families of polynomials that have been widely studied. And so aside from the Hagelin-Heyman-Lurf formula, there were other formulas by Ram and Yip in terms of AlCoVE paths and also Lennart. And the last fact is that there is also a non-symmetric version of Macdonald polynomials, which we call E mu. It's indexed by compositions. And this was introduced by Macdonald in '95 to study the P lambdas. Okay, so the connection between Macdonald polynomials and statistical mechanics has been known for quite some time, and many people have studied this. So, for example, Diaconis and Ram, they studied a probabilistic interpretation of Macdonald polynomials in 2010. And also around that time, Borden and Corwin studied Macdonald point processes. But most relevant to our interests is this theorem by Cantini, DeHere, and Wheeler from 2015, which says that when we set all variables except for t equal to 1, then we actually get the partition function of the ASEP on a circle of type lambda. So recall that the partition function is the sum over the unnormalized probabilities of the states of the ASEP. And also, when mu is a partition, then the non-symmetric Macdonald polynomial will specialize to the unnormalized probability of state mu of the ASEP. So what we have here is, on one side, we have these combinatorial objects and tableau formulas. And on the other side, we have ASEP dynamics. And so our goal was to study combinatorial objects that interpolate between these ASEP probabilities and Macdonald polynomials. So, so now I will talk about multiline Qs, which are those objects that are going to connect the probabilities to the Macdonald polynomials. So multiline Qs are a beautiful object that has been used to study probabilities of the ASEP. So in the case t equals 0, multiline Qs were first introduced by Ferrari and Martin, and also studied by Angel. And more recently, Martin discovered multiline Qs for general T, which I will describe now. So let's say we have particles of type 0 through L on an ASEP with n locations. So a multiline Q is a ball system on a cylinder with L rows and n columns. So in this case, L is 3, we have 3 rows, and n is 6. And on the cylinder, the first column is considered adjacent to the nth column. Okay, and a ball system is an arrangement of balls on the cylinder. And we also have a queuing algorithm which is an algorithm by which we pair balls in the row above to rows below. So each ball is going to take turns being paired to somebody below him. So for example, let's start with this ball. So he gets the label 3 because it starts in row 3. And it's going to travel to the right and keep traveling until it decides to stop and choose a ball below. and t is going to count how many available balls it has skipped during its journey. So if we suppose that it wrapped around j times, then it skipped exactly 3j plus 2 balls, because every time it wraps, it skips 3 balls, and then it also has to skip these 2 balls to get to that one. And so the total weight of this connection is 1 minus t times t to the 3j plus 2. The 1 minus t is just the common factor. So we can actually represent all possible pairings from this ball to that one with this infinite sum where j just ranges from 0 to infinity. And of course, we can write that as this one nice term where all we need to keep track of is the minimal number of balls that are skipped to get to this one. So that's 2. And in the denominator, we keep track of the total number of available balls in the row below. So in this case, that was 3.
Olya, just one question for the chat. Can particles hoop right, left, and up and down?
Sorry, can they what?
Can particles hoop right, left, and up, down?
I think can they hop is probably what it means.
Oh, no. So the balls are fixed. They're only choosing which ball to pair to in the row below.
Okay.
So the balls are not moving in this case.
Okay.
So this object is actually a lifting from the ASEP Markov chain. And I'll explain that. I'll explain how it relates to the ASEP shortly. Okay, so now the balls are going to take turns pairing to somebody below, and each connection is going to give us some factor in t. And so this ball, it starts at row 2, so it gets the label 2. And then these balls start at row 1, so they get the label 1. And finally, we're going to read off the state of the multiline queue that this system corresponds to by just reading the bottom row of the labels. So here, the bottom row of the labels is 2, 1, 0, 1, 3, 3. So this multiline queue is of type mu here. Okay, and so the beautiful theorem of James Martin says that the stationary probability of state mu of the ASEP is the sum over the weights of multiline queues whose bottom row is mu. So here's a quick example. So let's say mu is this state 2, 2, 1, 1, 0, 0. So we can write out all of the possible arrangements of balls and connections that give us 2, 2, 1, 1, 0, 0 as the bottom row. And we add up all of their weights, and we get the stationary probability of that state. Okay, and we have a corollary due to Cantini, Dehere, and Wheeler, which says that if we sum over all multiline queues whose particle type is lambda, then that equals the Macdonald polynomial with all its variables except for t set to 1. So the natural question here is, can we add the variables x1 through xn and q to our multiline queues to get the full Macdonald polynomial? And the answer is yes, we can. And actually, in a very natural way, it turns out, which was quite surprising. So the queue is going to keep track of how many times each ball wraps around when it pairs with the ball below. So each wrap is going to contribute q to the L minus R plus 1. So L is just the type of the ball, R is the row that it wraps from. So in this case, every time this one wraps around, it gets a single q. So we just put the q into this infinite sum, and we get this term here. So again, the weight for each pairing, all we need to count is the number of balls, the minimum number of balls skipped, whether or not the ball wrapped around, and the number of free balls. So in this way, we put the q's into the terms from all of our connections, as in the previous slide. And again, we read off the state from the bottom row. So the x's are also very, very natural to put into this model. So the x's are just going to keep track of how many balls are in each column. So here we have 2 balls in column 1, so we get x1 squared. 2 balls in column 2, x2 squared. 1 ball in column 3, it's x3, times the product of all of these connections. And so if you are familiar with the Hagelin-Heyman-Lur tableau formula, then you will notice that these terms look very similar to the terms that you would find in that formula. And I think that this multi-line Q model gives a very, very natural interpretation for where you get these Q's and T's. Okay, so the theorem is, so when mu is a partition, then the sum over all multi-line Q's with bottom row mu is the non-symmetric Macdonald polynomial. And in general, for general composition mu, we get permuted basement Macdonald polynomials. Oh, sorry. And for a partition lambda, we get the symmetric Macdonald polynomial P lambda by summing over all multi-line Q's, where mu is a permutation of lambda. And as a corollary, we recover James Martin's result and probabilities of the ASEP. Okay, so here's a quick example for P21. So we just look at all the multi-line Q's where there's 1, 2, a 1, and a 0. And we add up all their weights, and we get this polynomial. So it turns out that our formula is more compact than the other known formulas for Macdonald polynomials. So when all parts are distinct, then it's actually the same formula as HHL. But when there are repeated parts, then our formula is more compact. Okay.
Okay, I'm giving 1 minute warning here.
Okay. Okay, so inspired by multi-line Q's, we also have compact formula for modified Macdonald polynomials and a new quasisymmetric Macdonald polynomial. So I'll very quickly describe quasisymmetric functions, so which contain the symmetric functions. So recall that we define symmetric functions where the coefficient of any monomial is equal to the coefficient of that monomial with the indices permuted. And quasi-symmetric functions is the coefficient of any monomial where the indices are shifted is equal. So here's an example of quasi-symmetric polynomial. Okay, and this gives us a useful toolbox for studying symmetric functions. And we can define our quasi-symmetric Macdonald polynomial by taking the sum over all multi-line Q's whose non-zero particles are in the order gamma. So I'll just explain this through this example. So G21 is the sum over multi-line Qs whose bottom row is 210, 201, 021. So we can just insert the zeros in any position. And the main theorem is that these functions are quasisymmetric. They sum to Macdonald polynomials, and they are a QT generalization of the quasisymmetric Schur functions that were introduced by Hagelin, Lodo, Mason, and Van Willigenberg. So finally, I leave you with some open questions about properties and applications of these quasisymmetric functions. And thank you for listening.
Thank you, Olya. Let's give her a round of applause. Great, so we have time for one or two questions. Are there questions here that haven't been answered in the chat? Okay, do you use Derrida's matrix ansatz in proofs?
No, we actually used the Hecke algebras for this, affine Hecke algebras. So I have a slide for the method of proof. So the non-symmetric Macdonald polynomials, they're eigenfunctions of certain operators, and they satisfy some relations with respect to these operators. And what we prove is that our polynomials satisfy the same relations. And that is how we show that our polynomials coincide with the non-symmetric functions in the case when mu is a partition. And from there we get the rest.
We have two more questions appearing in the chat. Let's go in order. So another question from Jason Said. It says, do you think similar methods can get a formula for E mu when mu is any composition, not just a partition?
So that is actually a good question. So it would be interesting to see if we could get a multi-line Q type formula for E mu for other compositions. So in general, multi-line Qs give formulas for permuted basement non-symmetric Macdonald polynomials.
Cool. And we still have a couple minutes. So from Zach Hammaker, are your quasi-symmetric functions fundamental positive conjecturally?
They are not.
Okay.
But they're so we do have some non-positive expansion in terms of fundamentals.
Cool. And then from Gabriel Frieden, is there a Q generalization of the ASEP corresponding to your Q weights?
So that was my last open question. Currently, we don't know anything about that, and I mean that would be a very interesting question to answer.
Okay. And it looks like we still have a minute here. So can you extract a new combinatorial formula different from the Knapp-Sahi's one for Jack polynomials from your formula? That's another question here.
So I'm not sure. I have looked into that a little bit. And first of all, I'm not sure that I can get something different. Yeah, the answer is I don't know entirely. Yeah.
Okay, well, it seems like there's a lot of great questions here, and maybe I'll just pause it here and people can ask Olya more questions in the lunch break. And so we're going to now try to go to the other Zoom room for the lunch break. Thank you again, Olya, for a fantastic talk.